Hello then, so it's my pleasure to introduce to you our dynamic duo this evening, Dr. David Lauder and Dr. John Rogers from our EMC committee. They're going to be talking about a subject close to your heart, so I'm quite sure, locating and identifying interference. Over to you, John.
Thank you, Philip. Can you hear me? Thank you, Philip. Okay. I'm John Rogers. The better looking one is David Lauder. And what we want to do really is to pick up on a couple of other presentations that have been made today. The first one by Ian on how to keep RF out of your shack and how to get rid of noise. And then Tony Canning gave us some examples of the different types of noise you could see. We thought this year we would try and make it very, very simple and look at how you can locate and identify sources. So, what is electromagnetic radio frequency interference? That's the term we like to use. It's basically whereby you have a source of RF energy which can either be conducted or radiated to a victim which will pick it up, and its performance or the way it works will be impacted in some way by that radio frequency interference. The important thing is that conducted emissions not only applies to resistive connections, but it also applies to reactive connections. So if you have an inductance or a capacitance between the source and the victim, then it can still be a conducted emission. So, how do you locate a source? There are two different ways depending on whether it's nearby or further away. If it's nearby, the easiest way of doing it is to actually rely on signal strength. So, if I tune and I have a source of interference here, as I move closer to that source, so the volume goes up. I can reduce the gain and maybe the volume a little bit. But what you can do in practice then is to either put an attenuator if you're using a simple device like this, or you can reduce the effectiveness of the antenna, and what that will do is will allow you to work out where the source of interference is. If it happens to be a short wave radio, it can be an advantage because then you can turn to a different frequency. I was just looking for general RF hash there. And obviously in a room like this, it's very difficult to give a realistic demonstration with such a simple tool. You can use your little portable. The important thing is it has to be battery mounted, battery powered, and you have to be able to walk around, and you can either use a loop antenna or a whip antenna to try and work out where the noise is coming from. So you move in the direction of increasing signal, reduce the gain, and find the source. Once you've found the source, it's quite important to work out whether it is really what you're looking for or whether it's just another source you found that happens to be there. So the important thing, first of all, is to rule out very near field effects where they drop off very fast, and you can do that by just taking your signal strength as you move away a little bit, and you can eliminate them that way. But that isn't really very satisfactory. It's not a good way of doing it. It's something you can always do, but a better way of doing it is to use something that gives you a picture of the interference. Now here we're using an SDR, which is like the one on the table. We either use an E-field whip, like this one, as the antenna, or we can use an H-field loop, like that one, to pick up the interference. And this has just gone blank on me. And this gives you some idea of what you can see. So this is an E-field probe taken near to this computer. With the power supply turned off is the blue line, and with it turned on is the purple line. Similarly, the H field is shown here. The yellow is with it off and the green is with it on. And this helps you, A, to find what you're looking for, so that you can know when you're getting closer to it because it gets stronger. And secondly, you can check that the signature when you think you found a source is the one you're looking for. So if I come out of this, this setup is running here. This is looking at the H field in the room, and what you can do with it is you can set a trace, you can look for the peak, and then when you've got it, you can very simply hold that trace, hide a different trace, and there's the pattern that you're looking for. So now when you take your probe and you move around, you're only interested in whatever pattern is the one that's causing you interference. Is that clear? So it's a very simple technique that you can use to try and find the source. If I get rid of that and get the cursor back on this screen, which is always the problem, put that back up again, then you can see how that with either a very simple tool like an AM radio or a portable receiver, or with a simple spectrum analyzer running off a very reasonably priced SDR, you can actually track down something that's close to you. If it isn't close to you, or if it's more complex, let's have a look at maybe a more complex signature. This is a simple switch mode power supply for a computer, and that shows you how distinctive the signature can be, because all of these spikes here are coming from that Maplin switch mode power supply. So obviously if you're looking for that, as you move closer you can find it. This is a different display. This is on a traditional SDR, so you've got the amplitude at the top here, and you've got the time spread out at the bottom. So where's my pointer option gone? There it is. Because I stopped it, it disappeared. So up the top here we've got the spectrum at a given time, and here we've got the waterfall over time. However, once you've found what you're looking for, which is effectively all we've done so far, either with your little amateur receiver, your AM radio, or your spectrum analyzer, you then need to do some very important checks. The first one is it something in my house? If it is, it's a very simple way of proving it. Turn off the mains. Does it go away? Yes. Turn it back on again. Does it come back on again? Yes. Then turn it back on again one breaker at a time until you isolate what it is. And this is where it becomes important to know what you're looking for, because I can guarantee that with every breaker in that house you turn on, your noise level is going to ramp up. So if you don't know exactly what you're looking for, you'll probably find a noise source. Maybe a great idea to fix it, but it isn't what you started out trying to fix. So make sure nothing in your property is the source. To do this, you have to have a battery operated receiver or an SDR running on batteries, as that is. You have to turn off the mains, and you might like to consider some other things that could be causing the problem, like the telephone line, cable TV, UPSs. All of these will carry on running equipment if you don't turn them off as well. Even in one case that I found, a car in the drive was causing the interference, and moving it up the road got it far enough away for me to look for what I really wanted. Solar inverters, alarm systems, emergency lights. If it's still present when you've got rid of all possible sources on your property, you know it's somewhere else. So what you need to do, what else you can do, is you can actually check to see if it's still there if you use a different antenna. You can use an E field, a different distance, you can use an H field. All of these might help you to find what's the cause. If you want to make sure it's not something that everybody's seeing, then go a few hundred meters away. It might be a real transmission. I have had several examples where I've been asked to track down something which was actually a real transmission. It wasn't interference at all. Log the times and strengths of the interference so that you can work out what's being used when, and then listen or use an SDR to find out how bad it is. There is a leaflet which we have printed out here for you. It's EMC 04, our leaflet that describes what I'm talking about in this, which we'd like you to take a copy of when you go, please. If you're further away from the problem, then you might need to drive around or walk around a bit to find out where it is. And we set up for locating VDSL interference a car with that loop on the top, and we had a field strength logger, which is a professional piece of equipment that actually records the field strength and the position where that field strength is. We read them out of that equipment, it logs it on a PC, into Excel spreadsheet, used 3D maps, and we produced this heat map which shows the roads around where I live. And blue is good, very weak. Red is pretty horrible. Anybody like to guess where I live? Not quite at that end of the road, but just down here. The other thing I should say is that this is a specific spot frequency. When we did this testing, we did it above the notch, in the notch, below the notch, and got a separate map like this for each of them. So what happened on one frequency could be quite different on another one. But this shows you, when you're tracing real interference, just how bad it can be, because you're talking about the difference between here, where there is no VDSL, and up here, where there's serious VDSL, of about 20 to 30 dBs, and both of those numbers, in this case, are 50 dB microvolts per meter, and those who in the room know what that means. It means basically you can't hear anything on HF. So there's an example of the way that you can locate the source. Once you've got it, and you're pretty certain, how do you confirm it? You use the on-off-on test. Do you know what the on-off-on test is? Anybody have a guess? You turn it off, it goes away. You turn it back on again, and it comes back. Hopefully, unless it's gone into standby. All right? So you have to be careful with that. But that's a very simple test. When you are certain you've found it, use the on-off-on test. You also have to be very careful of artifacts in your test setup, like this one. If I can get it to come out of there. Then what you can do is, if I get rid of the controls so you can see the whole thing, very simple test setup like this, and we're looking at the screen, and all of a sudden all this interference appears. You see it? You could spend a long while looking for that if you didn't work out is what happens when you touch the touchpad on your PC. So what am I using today? A mouse. Also, currently, I'm running with the power supply in. If I take it out, you will find that the level of interference will drop. So I stressed battery operated. I'm now stressing, make sure that you understand your test setup before you go any further. Get back on the right screen. Put the slideshow back on again. And this is an example. I mean, I was running it live. This is a recording of the same thing. So here, this is this computer power supply, and you can see the difference between the yellow and the green, and the blue and the purple. This is in a quieter environment where you can see the true measures. And on this side, this is the Maplin power supply that I showed you the waterfall of earlier, which is much noisier. And this was the laptop running the touchpad. So, to quickly summarise, how do you identify the signatures? You find them. You have to be aware of false signals caused by artifacts. You can use attenuators because artifacts are not reduced, whereas the real signal is. You can confirm with the second receiver. You can look for harmonics. And you can use a loop antenna to improve the rejection of the typical noisy, hashy sources you get around here. Once you've done that, get a quick snapshot, compare it with the signature templates, and there's a very good program called SIG-ID Wiki. And what that does is it shows you what real signals look like so that you don't end up chasing real signals. Once you've got a snapshot, store it and then look for it. So these are some examples of snapshots. This is PLT, power line transfer. It's a modern one because its signature is these notches. Can you see them? And where do you think they are? In the emitter bands. So if you actually store your picture, have a look at it, look for notches in the emitter bands, that's the signature of PLT. On this side, these two big humps here, any idea what they're the signature of? They occur at the upstream, downstream bands of VDSL. So again, there's a clear signature there. I talked about SIG-ID Wiki. If you look it up, that's the sort of thing you'll see. This is for the amateur band, and it gives you an audio that you can play back and a spectrum waterfall, which will give you the signature that you can compare with. So you can eliminate all the real signals. Think that's bad? What do you think that might be? Tells you on there. That's in my kitchen, having put a pot of water on to boil on the stove. It's completely obliterating the long wave and medium wave transmissions. Then it up here, then it comes to the boil and it changes its resonance, and then it switches off and you can see all the signals underneath.
So is that an inductive pathway?
Yes?
Inductive cooking?
Yes.
Okay.
It's a domestic, boiling water in my kitchen. And we did this to take measurements to see how it dropped off, because we wanted frequencies around 70 to 80 kilohertz so that we could get an understanding of how they behaved as they went through a house. Guess what for? Wireless power transfer. So the last thing that you can do, and I haven't got time to show it, is as well as the H field and the E field, you can actually hook up a device to actually measure the conducted emissions. So with the simple equipment you see here, you can do all of the testing you need to do to identify and locate your sources. That's a massage. You've got a sore back. It's all right, as long as you don't mind 20 dBs of extra noise, you can use it. So that's the summary. What we want to do now is to actually stop the presentation and do some demonstration. The first thing is that David is going to talk about is a switch mode power supply. Should come on.
Okay, so yeah, so some of the things we'll be demonstrating in a few minutes. So switching power supplies, of course, are everywhere, and this is an example of a USB one with 5 volts out, and normally, well, for switching power supplies, the fundamentals normally below 150 kilohertz. So, so you can see the harmonics very clearly there. Now, a well-designed switching power supply will, the harmonics, 1, will be below the conducted emission limit, which these aren't, and 2, they will fall down and down and down. And by the time you get to 10 megahertz, they will typically be 20 dB or so down. if it comes up as you go up in frequency, that is characteristic of a poorly designed supply or missing out a particular capacitor that should be fitted. So you can, it's worth having a look in long wave broadcast band. You'll normally find a harmonic there somewhere with 100 hertz buzz. And things with the long wires attached. We've got one here that is used with an outdoor security camera, and we'll show you in a demo the effect of attaching a long wire to it, to the DC output, like 7.5 meters compared to, say, something like a mobile phone charger, which is just a meter or so. Okay.
Space bar.
LED lamps. Now, of course, LED lamps, some of them are linear power supplies and completely silent, but most of them are switching, and it's a miniature switching power supply, but doesn't necessarily produce a miniature level of radio interference. So in this case, the ones that we've identified as being some of the noisiest available are, the fundamental is just below 200 kilohertz, so it's perfectly placed to interfere with radio for long wave on 198. It was obviously designed in a country where they don't have long wave broadcasting, and it was designed with a complete disregard for EN 55015, which is the relevant EMC standard. So we've seen things that are 40 dB above the limit down here at the fundamental at around 200 kilohertz, and the best one is 10, 20, 30 dB below. So from there, from say 33 to 110, that's over 70 dB difference between the best and the worst. The best is well below the limit, it must be said. So I think we can probably say, if you can work out that the fundamentals around about 200 kilohertz, then it's probably more likely to be something small like an LED lamp rather than a fully fledged switching power supply for, say, a laptop or something like that. It has been known for these things to put RFI up to VHF and 50 and 144 megahertz amateur band, and in some cases DAB as well. So without further ado, I will move on to some oh well, John's just going to sum up and then we'll do the demonstrations.
No, I'll come back to that. We'll do some demonstrations now, and the first one David will set up while I set this side up. I'll take one question while we're setting up, if you like. Does anybody have a question?
I noticed that the CE mark is invalid, basically, on that last slide.
Okay.
Sorry.
That's all right.
Yeah, Dave Howell, M0VTG. I noticed that although it's supposed to comply on that last slide with an EN standard, and it was marked CE, it was absolutely useless piece of kit and it has an LED from our perspective. So don't believe in crap electronics, if you like, or Chinese electronics, whichever you prefer.
Well, it's symptomatic of a lack of enforcement by trading standards. You try to get trading standards to do anything about this, but also, of course, you can buy these things on eBay. You can bypass the importers into the European Union, and you can import stuff that is non-compliant, and it's up to you. You're not placing it on the market, but you are taking it into service, so you are, in theory, responsible if there's any interference. Right, okay, so I'm going to plug that in there.
I could do, but it's currently plugged into the wrong...
Right, so this is a homebrew listen, a line impedance stabilizing network, which basically measures the conducted emissions onto the mains. And so we have here a very nice LED light bulb. It was the quiet one from the demo.
I've just got to swap over to the other input to the spectrum analyzer.
So yeah, so we're going to do. We want span 2 megahertz and center about 1. Okay, so that's a good one. And now. That's made by Philips, by the way. This one is not so good. It is, however, not the worst. The worst that we've found is actually the same brand. And what they've done, so we need to change the reference level to -20 probably.
Yeah, I just want to compare them first, David.
Mm.
So that was the first one, that was the second one, and this is the third one.
So it's absolutely end stop. It's not only got no RF interference filtering, but it's also got no smoothing capacitor. So it puts out an awful lot of ripple onto the mains, and there's no filter to stop it. Well, there we are. So that's LED lighting for you. Now let's look at. Pardon? Oh, I've got the boxes over here. Well, the good one is Philips, and it's well below the limit. We've got 2 here that are called Super LED, and I have to say they are not super quiet. Right, okay.
And what I've just done there is expand it to the screen, taking a screenshot of it, so I've got that for reference later.
Now, this is a USB power supply. So we need a new. Okay. So this is a genuine Apple iPhone charger, and with a 1 amp load on it. And we know it's a genuine Apple iPhone charger because if you look in the USB socket, you can see a serial number. So that's down at 30, what is it? I don't know, minus, or in dBm here, minus 70 dBm. There's 20 dB of attenuation in this listen. So now look. And this is one that the sort that you can get on eBay for a few pounds. As you can see, it is somewhat noisier. And watch what happens to put it on. Right, now watch what happens if I ground the center tap of the DC output. So what you do with the DC output makes a difference, whether you connect it to a long wire or a short wire. And grounding the, effectively the center tap gives simulates the worst case situation with a long wire. Okay, and finally, let's have a look on 14 megahertz now with the Wellbrook loop. Is that easy to?
I'll take a question and then I'll do it.
Okay.
Is there something else you want to do first, or?
No, that's the next
Okay.
thing. Yeah.
Yep. Well, do you want to take the mic round? When anybody got a question for us?
Thanks.
Sorry. Two staggers for the past week. Terry Chipperfield, G3 VFC. You say that trading standards and similar don't want to know. Has the RSGB EMC committee approached the Consumer Association, which to get them to amass a load of complaints and make a super complaint? Are there enough amateurs who could be persuaded to approach which and make that super complaint?
I think that the idea of approaching which has been used on some occasions. Hilary is nodding because it was before my time on the committee, and Donna's nodding. At present, we are, you may have noticed, we've had a big meeting with Ofcom, at which we've challenged them, and we've got them to admit that VDSL does cause an electromagnetic disturbance of a level that might interfere with amateur reception, which is their wording, not mine. What they won't accept is that that is harmful interference, so they don't have to enforce it. Similarly, with trading standards, we've approached them in the past. What we need to do now is to mount a really strong campaign, which we're going to do, and we are going to consider all options, come up with the ones that we think are the most likely to have some impact, and then take those up for approval and implementation. And certainly which is one possible venue. Thank you.
Yeah, so we did have a meeting with Which specifically about LED lights. Their interest was that they're causing interference to DAB. You switch your LED lights on, your DAB radio goes off. That's a very different situation from this thing down, at stop band and 80 meters, which are particularly badly affected with some of these ones. So actually, trading standards, it's theoretically their responsibility, but they don't have the resources or the expertise. They've got so much work on with stuff, trying to enforce against stuff that's electrically unsafe, that EMC comes down the priority list, although some of the stuff that is causing interference, when we look at it, we can also find that it's electrically unsafe. So it is actually Ofcom's responsibility, as well as trading standards, and it should be possible to persuade Ofcom to take action. They used to have a lab at Whiteleaf where they had test equipment and they would investigate things like this, but they closed that.
Okay, so we'll come to the question in a second. This is showing the Wellbrook loop over there at about 5 meters. I think nulled on it as well. So I had a question at the back.
Yes, Tony G3OVH. I had an experience with my mother-in-law's LED lamp. It was one of these with a touch sensitive base, and it could either be warm white or bright white. And her FM radio that was close by always turned off when she lost Radio 4 or Radio 2. So I took it off her, and I couldn't get the bass off. It took me, I put it to one side. Eventually I managed to get the bass off, and I found it was the built-in clock that was inside the it would show sort of time or temperature in the upright of this lamp, and it had a small switch mode power supply, which was clearly useless. When I disconnected that, which she didn't need, the LED lamp itself was fine. It was as quiet as anything. So sometimes you can modify these things so they do the job that you want them for, and the ancillary bits, which was also a USB charger built in, once it was disconnected, it worked perfectly.
Okay, thank you. Any other questions?
Dave, G3YX. Has anybody investigated those double main sockets with inbuilt USB power supplies? They worry me because they're permanently powered. You can't switch them off. And if they start causing interference, we're stuffed.
I don't know of anybody who's done them. Have you done any tests, David?
No, we are aware of the widespread use of USB outlets on main sockets, and even you can get four-way extension trailing sockets with USB built in. No, but it's something that I would be interested in any reports, and it's certainly something we can test for the EMC column. So the last demo is a Class D audio amplifier. Now, this is the speaker lead, one of the speaker leads and antenna, and then we're picking it up over here on the loop. So you can find these in a media bed, which is available from well-known high street bed retailers who don't seem to have got much knowledge of EMC, because, as you know, Class D amplifiers, unless they have good RF filtering on the speaker outputs, are going to cause interference, and this one certainly does, because the interference filtering is non-existent. And it puts up a big signal in, it's quite narrow band, puts up a big signal in 14 meg amateur band. For some reason it's sort of shutting down because it's possibly because it's decided it hasn't got a speaker connected or something like that.
I'm also rotating this to try and peak it. So.
Yeah, you might be best to turn it 90 degrees to what it is now. You might be on a null there. So, but you'll know if you've got one of these because it's been in Radcom, and it will, when the audio amp is in use, because it's pulse width modulation, if you listen on AM, you'll hear the audio in that's being transmitted by the Class D amplifier. In fact, somebody, when we first came across this, the person who reported it thought that it was a HF broadcast station operating in the amateur band, but it wasn't. Not an intentional broadcast anyway.
Okay, any other questions? Tony.
Does that
wait. Sorry.
Hi. Tony Canning, G2NF. Does the device you've just demonstrated, does it also apply to PC speakers, for example, where they have Class D amplifiers in them? Little things you can buy on the side of your speaker, either side of your laptop to play music on.
Inevitably, everything will radiate if it's got the Class D amp in it, but this one was particularly annoying because it was so strong, basically. And in fact, the second case of this we've had is currently taking Ofcom to the Ombudsman for not tracing it properly. So this was and when they traced it, they proved it was that by turning it off, but then Ofcom refused to do anything about it. So he's taken them to the Ombudsman at the moment. So it's not us. Because it's not RSGB who has the problem, all we can do is help our members in their application of the problem. We can't, unless it was a fault at HQ or at the NRC, then it would be us who were a problem. We can represent their opinions with Ofcom, but we can't make a formal complaint.
Andrew Bryant, I don't have a call sign. I came slightly late. I gathered your talk was about interference on radio bands. What exactly does EMC stand for?
EMC is, the reason I don't use it, and I kept using RFI, is EMC is actually what stops the problem, not what causes it. Electromagnetic compatibility, if you have insufficient level of radiation or conduction to cause a problem, and you have sufficient immunity, that's what electromagnetic compatibility is about. It's basically there to kill RFI. So anybody who talks about EMC and says, do we want to get rid of EMC? No, thank you. We want to keep it, we want to strengthen it, because it's that will allow us to enforce problems with RFI. Okay, we've got to wrap up. One last question.
No, I'm not seeing hands, so we'll draw it to a close there, if we may.
Did Don want to make a comment about WPT?
He's got 30 seconds if he does.
Okay, that's all right. We also have apologies from our current chair, Martin Sack, because he's out at the moment attending a standards meeting, which is the other half of what EMC does, EMC committee, in trying to enforce the right standards such that the problems don't occur in the first place.
We couldn't Skype him in because he's in the wrong time zone in Shanghai. Thank you very much, everybody, and thank you very much for your splendid presentation.